Welcome to Banks Unboxing, where every day is Christmas. A lot of guys break DURAMAX crankshafts, but I'm not one of them, and I'm going to show you why. So the UPS and FedEx guys are getting to know me. I'm out on the curb like a dog waiting for food when they bring these special packages. And here's the latest one, and this is from Vibra-tech TVD in Buffalo, New York area, owned by the Herschel brothers. And this is another family operation. The brothers are Carl and Louis, and Louis' son and daughter work there. Carl's son works there, and about 12 other Herschel relatives work there. God, I love it. I absolutely love it. So let's see what we've got here. Now, this is probably going to dull the blade because I think I've got some staples in here. Oh, man. Oh, shit. Oh, always defeating me. Cutting the tape is not going to be. Jesus. Okay. I think I got a little staple work to do here. First, we have to find the staples. Then, once we find the staples, it's like an archaeological dig or something. Here we go, here we go. Vibra-tech TVD is the maker of Fluidampr products. And they're also the maker of Banks vibration dampeners, Viscous in both cases. This is something that we're kind of doing together, but generally we design what we're looking for in terms of our damper, and then some science is applied. And that science has to do with determination of the mass of the damper. This is what I call the hub and they call the damper. And once again, I'm going to have to, there we go. There now. Amazing what a little leverage will do for you. All right, that's the bolts. This is going to be a beautifully executed piece of machinery here. All right. There's the friction washer. This is a diamond dust friction washer that helps drive the damper. In this case, we're looking at what I call the hub. And there we go. So this baby mounts on the crankshaft first. This is the face that's towards the engine. So this friction washer goes between here and the gear on the crankshaft. And what the friction washer does is it gives you a friction couple. So when you tighten down the retaining bolt for this assembly, most of the torque, in fact, virtually all the torque, is transmitted through this surface to the corresponding surface. There's two keyways. We've double keyed this setup. We've marked where the original equipment keyway is so that you don't end up putting the wrong key and putting the thing 180 degrees out because it's got a counterweight, and you want the counterweight to be counterweighting properly. This is the standard belt plane for a DURAMAX L5P, 6-rib, but it's smaller than standard because we're going to be turning the engine faster. We kind of brought this diameter down to slow the belt down 10%. We're going to take the engine from 2,800 RPM to 3,800 RPM. I felt that would drive the accessories a little too fast, so I took 10% off here to help compensate for some of that, not all of it. We don't want to slow down the alternator too much at idle, or it won't be producing enough amperage. Also on this is our drive pin setup that we pioneered some years ago here at Banks. And this allows you to put the damper on and install the bolts, but the bolts don't position the damper, and the bolts don't take the drive torque that comes through this hub and into the damper. So you're not shearing off the bolts. There's no slip. These pins go into receiving bores on the damper. So next box to open is going to be the damper itself. All right. So they sent no instructions because we're the guys who designed the damn thing. We had to know how to do the deal, but the SFI is a big deal in that this is a legal racing product. And that's exactly what this assembly is for. It's to go racing and not break the crankshaft, because in my opinion, the viscous damper is the only way to go. And I'll tell you a little bit more about that in a minute. So what's cool here is a couple of things. First of all, as I mentioned, so there's the drive pins, and they engage in the back of the damper. So the back of 3 of the bolt holes on the front. So you can still put the bolts in to retain a pulley or a set of pulleys on the front if you so desire. There are 6 bolts that retain the damper to the drive hub, and then 6 other bolt holes to allow you to put a blower pulley, a pump drive of some kind. Maybe you've got a cooling system that you want to have an auxiliary pump on, or maybe you're pumping liquid coupled intercooler water at 100 gallons a minute, something like that. And one more thing here, the outside diameter is a 12 rib flat belt drive, 8.5-inch diameter pulley. I want to drive blowers or or maybe superchargers with that 12 rib. And I'm working with Whipple. He's got a new blower coming that this will be driving. So I know this is shiny and it's awesome, but what does it do? Well, it damps vibrations that are put into the crankshaft by the firing of the engine. That's the dominant source of the energy that makes the crankshaft vibrate. When the cylinders fire, they twist the crankshaft, the crank arm. And it might be best to get a crankshaft on the table. But before I do that, let's do another unboxing. Proto Labs, these guys do prototype CNC work for us when we can't get to it over in our production shop. All right. What have we got here? This should be for the crank trigger. What we're doing with the L5P is we're taking the crank trigger off the back end of the crank and we're putting it up front. That way we can have a standard racing counterweight on the back. I'll show you the L5P crankshaft and our big pin crankshaft and why I'm doing this crank trigger the way I'm doing it in just a moment. This bracket mounts the crank sensor that's in the back of the block. So the first thing we do is we make a plug for where the crank sensor currently exists. That prevents oil from coming. It would become the oil hole, you know. Guy came into my speed shop one time, bunch of people at the counter. He says, there's oil all over the street. I want you to come and look at it and tell me where the oil is coming from. And I said, I can tell you right now. It's coming out of the oil hole. He didn't think much of my humor. So here's the OE sensor. It plugs in here, and this mounts on the front timing cover. And once it's mounted, it looks something like this. So there you have the crank trigger, and this is the trigger assembly, which once it's installed on the crankshaft, positions something like this with a proper air gap. Now you have a front trigger assembly built in to the mounting hub for the vibration damper. All right, I've cleared this off because I want to show you a stock L5P crank. Ah, okay. So here is the timing wheel or trigger wheel on the back throw of the crankshaft. What's compromised here is the counterweight mass, and I don't want to compromise it. What I'm trying to do ultimately is bring as much mass inside and not have the counterweights on the outside as originally designed. Well, why do I want to do that? The bending moment on the nose of the crank is why I want to do that. So let me get this baby around here. And essentially what happens when you have a counterweight out here, and we've put the stock counterweight mass into the assembly, as the RPM increases, that counterweight torques the nose of the crank. It puts a bending moment on the nose of the crank. And we did a little math on this. At 6,000 RPM, with this mass, the bending moment is 7,200 pounds. The crank is being bent in the direction of the counterweight, and it's using the first main bearing as a fulcrum and putting force, bending moment, through the front rod journal into the second main. How do we know all of this? Well, because we destroyed one. We got to 6,300 RPM, full counterweight mass. I didn't think the bending moment would be that bad. It was. And we actually kind of ruined the front main, but we totally destroyed the second main. We didn't break the crank in that it was a Bryant billet crankshaft that Sonny makes for me for these engines. Here's what it looks like when you break a stock crankshaft at the front throw. This is usually caused by the external counterweight, especially if you've defeated the governor, you're upping the RPM, and you're running a stock counterweighted damper. To a lesser extent, this can be caused by the firing order of the engine. The problem here is this can happen without the bending moment of this counterweight. Guys have done it with internally balanced crankshafts as well. We're doing two versions of this, by the way, with and without counterweight. This version allows you to put this on a stock crank assembly, and you don't have to rebalance the rotating and reciprocating parts. It's OEM balance. And how do we know that? Because after it was machined, it was set up on a balancing machine at Vibra-tech, and they confirmed that the out of balance condition of this counterweighted hub was same as stock. This thing can go right on, and this thing is going to go right on our Killing a DURAMAX engine. We've noticed that the stock damper is starting to go away, and it's what's called a rubber or elastomeric damper. And I've got one right here. So this is a stock 17 to 19 L5P damper. Counterweighting's a little different, but what I really want to show you It has an inertial ring, and it has a rubber section in here. When the cylinders fire, they put rotation into the crankshaft. I've shown you the stock crankshaft. Now, through the magic of editing, I'd like to show you a Banks crankshaft. Ah, here we are. All right, this is the Banks Big Pin DURAMAX crankshaft. We came out with these for our own use, maybe 5 or 6 years ago. What I wanted to do on this crankshaft was increase the rod journal, because this is a stroker. So we're moving the pins out to give a longer stroke, and with a 0.5 millimeter overbore, this takes the engine from 6.6 liters to exactly 7 liters. Making the pins larger enabled me to have the same pin to main, in fact, a little more pin to main overlap between this surface and the main surface. So where the metal flows directly through. As you stroke the crank, that overlap decreases and the crank becomes weaker and more easy to break in the throws. We came up with our own bearings, a rod bearing diameter that has never been done anywhere on the planet. Then we designed our connecting rod, and the big end of the rod is now big enough that if the rod was a conventional design, you couldn't get it through the bore to assemble the engine. So we canted the big end, the split line, so that with the cap off, rod goes right through. This is not an uncommon thing. They've been doing it in diesel engines for decades, but not in a DURAMAX. We can vary the rod length. We want to put the big pin crank in the L5P. I want to have full rear counterweight capabilities. And the rear counterweight mass is the biggest counterweight mass on the crankshaft. Not putting the trigger wheel back here like they do on the stock crank and putting it out front as we're doing here enables us to put a pure racing crankshaft into an L5P. And in the not too distant future, this stuff will be available for you. So let me rotate the crankshaft a little bit, and I will explain the torsionals to you. Imagine a con rod connected here, going up to a piston in a bore. As the cylinder fires, it starts pushing on this pin, and it pushes it all the way to bottom dead center, or close to that. The exhaust valve opens before bottom dead center, so it takes away the push. But that push goes all the way through the crankshaft. Much like it's a torsion bar, it twists the crankshaft. And after the firing stops, it springs back. Well, what's going on is this twist has to travel through the crankshaft. It accelerates the flywheel mass, the torque converter or clutch mass, everything through the transmission, through the prop shaft, to the differential, out the axles, to the tires, and the tires try to rotate the world. That's what's anchoring the back end of the crank. If you're trying to rotate the world with the tires, and you're trying to do it from the first throw on the crankshaft, you've put a lot of energy through the crank. Basically, you don't want it to reverberate or resonate or continue to vibrate. What does that look like? Well, in the most elemental way to show you that would be with a torsion bar that has a damper but no inertial ring. In other words, a flywheel, so to speak, and then a viscous damper on the same torsion bar, both preloaded the same amount and then released. So you've got this preload on this damper or little flywheel, and on the left you'll see the flywheel, the undamped setup, and on the right you'll see the viscous damped setup, and they're both released at the same time with an arm like the arm on a one-armed bandit, you know, a slot machine. Here he pulls the pin. See, they both start to vibrate back and forth. But watch the one on the right and see how it's starting to slow down now. And finally, it comes to stop, and the undamped one is still oscillating. That's why you want a damper on the front of the crankshaft. You don't want that to continue because you're putting pulses into other throws of the crankshaft. This gets very complex if it's undamped. The crankshaft is held in to basically a straight line because in this complexity of power pulses being put into the throws and moving back and forth through the crankshaft, the crank wants to distort, if you will, axially or on its center line. It wants to distort. What keeps it from distorting? The main bearings, the main bearing caps. So here we're looking at the bottom of a DURAMAX block. You see what I'm talking about. There's 5 main bearing caps there. The first thing you'll notice if your crankshaft is not properly damped with a proper damper is it'll start kicking out the mains. It'll start killing the main bearings. And if you see that occurring, I'm telling you, you got the wrong damper. So we have 2 damper types. One has a center hub, a layer of elastomer, rubber, and an outer inertial ring. So as the cylinder fires, viewed from the front, it rotates clockwise. So this hub rotates, it distorts the rubber, and then finally the ring comes along with it. This can be tuned to various frequencies, but it has a narrow range of vibration frequency that it can be tuned to, a range of about 50 hertz or 50 cycles per second. The viscous damper has an inertial ring inside the body of the damper, and the gap between the ring and the housing is filled with a silicon fluid. This idea of a viscous damper dates from 1910. But the idea of a viscous damper really came of age in the mid-40s when Dow Corning invented silicone. The silicone used in here is about 45,000 times thicker than 30-weight oil. And it's temperature stable. This is the beauty of the silicone fluid. Unlike the rubber, which goes away with temperature, dies, or changes its durometer with temperature, which has a negative effect, this fluid can go from like freezing to hundreds of degrees and have the same shear constant. So it means that the damper has constant performance level and stays at the frequency you've tuned for a lot better through the temperature range. What happens in here is the damper housing is accelerated as the power goes into the crank pin. It's accelerated. The inertial ring is only coupled to the housing through the fluid, so the fluid shears. It takes the energy of that instantaneous acceleration and converts it to heat. How is this tunable? Well, if you look at the cross-section, it's tunable in a variety of ways. You can change the mass of the inertial ring. You can change its diameter or width within the constraints of the engine design. You can change the material. It could be cast iron, steel, bronze. They have different densities. So with the same geometry, it would have different inertia due to different mass. You can change the viscosity of the viscous fluid, and you can change the inside, outside, and side gaps. So you've got more viscous fluid or less viscous fluid, which gives you a different couple of the ring to the housing when that shearing takes place. So the thing is very tunable. How you tune it is a bit of magic. What we do is we measure the crank twist with the engine running. So how do we measure that? Well, we set up a trigger wheel, front and rear, with a laser optic system you find the worst case, the worst spot, the highest amplitude, the highest crank twist. You tune for that if you're doing an elastomeric damper. Elastomeric dampers have a very narrow window where they're effective. And it's usually a window of about 50 hertz. I did some calcs here on a V8. At 6,000 RPM, 4 per rev, that gives you 24,000 hits per minute on the crank pins. If you can imagine, that thing per minute is absorbing 24,000 torque inputs coming in through the crank pins. Per second, you divide that by 60, and you have 400 hits per second. If you have an elastomeric damper, in your bad spot, let's say it's at 3,750 RPM, which is 250 hits per second, or if your sensitive spot was 3,750 RPM, you have a window of 50 hertz. That is 750 RPM. Your window of effectiveness on a typical elastomeric damper is 750 RPM on the V8. So if you have secondary peaks, and they are there, it's not going to deal with them. The viscous damper doesn't have a narrow window. It's broad-based. Imagine this. The OEM damper is tuned for the stock crankshaft, the stock cylinder pressure, which determines the amount of twist. You're now hot rodding the engine, and you're putting a hell of a lot more twist into the crankshaft. What happens to the rubber when that happens? Well, it's happening on my Killing a DURAMAX series. We're at 3,300 RPM and 852 horsepower, and we have a stock damper on the engine, and I can see the rubber's going to hell. But before you can even see the rubber going to hell, you've hot rodded it, you're making more cylinder pressure, that makes more horsepower and torque. You start putting more energy into that rubber, it gets hot, it changes the durometer of the rubber. You can't see that happen, but it moves, it makes the rubber softer or harder, it changes the durometer, and it moves the tune-up or the critical point where this is damping to another RPM where the peak isn't. So right away, a stock damper is not a good thing if you're just hot rodding the stock engine. But if you change the crankshaft and you get serious with the internal parts, it's not even in consideration. So that brings us to the viscous damper. The viscous damper is tuned, once again, for that peak problem, that peak RPM, but it's broad band. This thing damps everywhere. So why wouldn't they do this rather than this? Well, this is a lot less expensive. But if you're spending money on an engine assembly or spending money on compound turbos and all this other stuff, you really don't want to break the crankshaft. It's pretty catastrophic. Your turbos might still be okay, but everything else is, you can put it in a bag. Here, sorry lady, here, I'll put it in a bag for you. I don't care if it's elastomer, it has a narrow tuning window. Outside that window, it's not doing too well. With a viscous damper, you can change the tune-up, you can change the cylinder pressure, you can change the intercooler, more cylinder pressure, and you can know that the engine will continue to operate in a safe environment in terms of vibration. All right, next stop for this damper, Killing a DURAMAX and Dyno 2. Stay tuned.